Yeah, hello everyone, and welcome to this session. So my name is Timothy Hunter, and it will be my pleasure to talk to you about deep learning and deep learning integration with Spark. So just to give you a little bit of background, I've been a software engineer at Databricks for about 3 years now. And in the meantime, I've contributed to Spark, and I am one of the main contributors also to graph frames, so the data frames-based graph wrapper for Spark, and also to TensorFrames, which is another wrapper between TensorFlow and Spark. And I did most of my research at UC Berkeley on doing what was back then a complete sci-fi project combining Spark, this absolutely unknown technology, and to show that you could do some machine learning on it. Back then, it was unheard of. Things have changed a bit since then. So today, I expect that everyone in this room has heard about deep learning at some point. And I would like to talk about not only one framework, but the kind of lessons that one can have when trying to use deep learning in the field, especially when you want to combine that with other technologies such as Spark. And so especially I would like to touch on the point of tuning Spark to make sure that it works well for deep learning application, especially in the context of GPUs, and also how you can make deep learning and deep learning frameworks and Spark interact together as far as data communication is concerned. So if you look at at last year, I would like to do a quick retrospective, and you can see really that it was the year of emergence of technological solution to combine deep learning and Spark. I did a brief count at the Spark Summit, and just last year, I could count 6 talks on deep learning, 3 talks on GPUs, on related hardware. And if you look at all these talks, there is not really a consensus as to what would be the best way to combine the Spark and deep learning. Because if you look at MLlib, the official machine learning library for Spark, it supports a fairly limited amount of technologies and framework and neural network patterns that you like to see, so mostly perceptron-like networks. And when you look at most of the talks that have been done recently, most of them introduce their own frameworks. And it's hard to figure out what is a more overall tendency as to what would be a good framework. So also it begs, so one thing then that we can look at is how many ways you have to combine Spark and deep learning frameworks. So these are all the ones I know of, and Alexei from Salesforce just mentioned yet another one that I don't know yet about. So you can see how fast this field is evolving now. So you have the usual common frameworks that are being used just for doing deep learning, and then that people try to retrofit into a Spark environment, such as Caffe, Keras, MXNet, Paddle, TensorFlow. Most of them have some integration with and some bindings with Spark. You also have nowadays frameworks that are becoming more integrated directly with Spark, especially BigDL, Deep Learning for J, DeepDist. And these frameworks try to rely directly on Spark for the communication patterns and doing the exchanges between the different phases. And finally, when we start to see also some vendors trying to accelerate communication and specific algorithms for their deep learning problems by trying to leverage specialized hardware, not even GPUs. And I can think of, and especially GPUs. I can think of 2 examples here, Blaze from UCLA and the IBM efforts for integrating GPUs with Spark in their conductor platform. So when you see this huge list like this, it really brings the question, can we try to go to the mythical one framework for doing deep learning that will rule them all and solve all the solutions we ever had. Because after all, this is the promise that deep learning are doing. It's going to solve all the AI problems. And so let me bring here a Databricks perspective. So Databricks is a Spark vendor sitting on the top of a public cloud. And nowadays, it provides GPU instances, especially for supporting deep learning workloads. Because if you want to run them at scale and efficiently, one of the most efficient ways of doing that is to use GPUs. So we have enabled customers to use to run these compute-intensive workloads. And this talk will be about the lessons we have learned when deploying these GPU instances on the public cloud, so not on the private environment. And also, what kind of limitation we have found in Spark when we have seen people trying to leverage these GPUs for running and deep learning frameworks for running deep learning computations. So really, what we hope to see happening in the Spark community in the next year. So there are all these frameworks, and so I would like to ask you the question: what are the considerations that we need to have in mind when we evaluate a deep learning framework, especially when you want to work in a cluster and integrate it with Spark? So there's performance, of course. That's usually the primary way that people have to compare deep learning frameworks, but there is also a lot of other aspects to consider in practice, because performance is only one aspect. And I really like this image from a Google paper published at NIPS last year, which showed how machine learning, as we think about it, is really the core algorithms that power most of data science, represents really a fraction of what you have to develop if you have to do if you want to move into a production environment. And in this case, you need to consider everything around. So not only the usual aspect of collections, transformations, featureization, and so on, but also all the aspects related to metrics, configuration, deployment, and also especially monitoring. So, and deep learning comes with their own set of challenges that in order to fit into this diagram. So, what kind of patterns do we see when people want to run deep learning? Typically, we have what we have seen so far is mostly two patterns. One of them is during the training phase, integrating deep learning as yet another algorithm to produce machine learning models, and the other one being applying these models afterwards to augment their data. So in a typical training task, people build a pipeline of more or less complicated, which starts by doing data collection, then with some usual transforms to perform ETL. This data at this point needs to be put in some form that is more amenable for machine learning and especially deep learning. And then once all this data is condensed into a model that is appropriate for the business case, it is validated, and then it is exported to some other systems. And if you look at this pipeline, you have fairly different set of requirements when you want to build it, especially when you want to provision the hardware or the underlying stack. The first phases where you collect data and when you perform preliminary transforms, usually these phases are very communication intensive. You move a lot of data. Deep learning, on the other hand, tends to be mostly used on a very small cluster, sometimes even one extremely beefy machine. And it doesn't require as much memory or as much communication necessarily compared to the other phases before. So when you're thinking about it from an integration perspective, this brings a fairly different set of challenges compared to just thinking about the ETL in Spark, for example. The second typical usage that we see is to transform some data. So in this case, usually the data has been already collected, and all we do here is, given a set of fairly complex input, such as images, we want to augment it with for example, labels or additional information, using, in this case, neural networks. And this is a fairly different use case from before, because when you look at this, every image or every input feature can be processed independently, and it only needs to be processed once, compared to the training in which you do typically multiple passes over the data. So in that case, it is less clear whether you are going to be constrained by the I/O, by the communication, or by the computational intensity of running neural networks. So when we look into how to integrate Spark with these deep learning frameworks, we see a couple of patterns emerging in terms of code architecture and algorithms being used. The simplest is usually how that people, and this is really the most common, people use Spark simply as a scheduler. So in this case, the machine learning, so the deep learning frameworks are simply run inside embarrassingly parallel tasks, and the data itself, which can be fairly large, is stored outside Spark, inside the so on the cluster or on the nodes of the cluster. The next level that we see is once people have learned models, or even want to reuse publicly available models like Google's Inception, for example. They want to augment this data, as I was mentioning, during the transforming phase, during the ETL. And in this case, the data usually comes in from data frames or RDDs, because it not only contains a complex part like an image, but also it contains all the other additional information that people have collected that contains some contextual information about this image, for example. And when you want, and this usually follows a different mindset, because in this case, when you want to apply this transform, you do not want to lose data. You want to make sure that whatever comes in is going to be processed and then stored later. If you use Spark as a scheduler, the data can be put around your cluster, and since you are doing it manually, you may actually not want to use Spark for making sure that you have some guarantees there. And finally, we have seen some usages which are a bit more advanced, in which people want to simply forego the benefit that Spark brings at scale. And in this case, people want to run specialized computations that may do one or multiple passes over the data set, and that follow specific communication patterns that do not fit inside the typical Spark framework. So for the first choice, when you want to run your computation by doing embarrassingly parallel tasks, a very popular choice is simply to use Apache Spark. Why would people want to do that? Well, a lot of deep learning frameworks usually have a Python interface, so you can think of Caffe, Theano, and so on. And in this case, you can simply embed your computation inside a Python program or a Python function and then let it go. So in this case, Spark really acts as scheduling black boxes, both for the data and for the computation. However, we found that people tend to hit some limitations when they do that, because when you look at how these frameworks are implemented, they are loaded as Python packages inside a Python process. And these packages assume that in general that their lifetime is going to be the process, so not the task. And this requires a few configuration tweaks in Spark, the most important of which, if you use this configuration, is probably to set the number of executor cores for each of the machines to 1. So why would you want to do that? Mostly because the deep learning frameworks usually gather a lot of information about the machine you are using to run these computations. And especially, it is able to leverage all the hardware directly. And when they have complex computations to run, they can pipeline these operations in a very efficient manner. So and this is more efficient than trying to use Spark to combine together these multiple tasks at one, because in this case, you will have contention between the task and break the pipelining that will happen on each of the processors, or even each of the GPUs. So this is probably one of the most important things that you can do to optimize the performance of your pipelining. So this is one pattern. The other one that we see coming fairly often is the use of cooperative frameworks. In this case, this is typically when people want to use a parameter server or other stacks such as deep learning for J. So in this case, the data comes in from an RDD, and then some computation happen, and eventually the Spark takes over the control back again on the computations. And in between, a lot of things may happen that may not follow the standards RDD guarantees. Typically, these computations are run in an asynchronous manner and cannot be then do not have any lineage information that would allow them to be rerun if one node dies. So why would you want to do that? Since you bypass Spark, that means you can efficiently move data without marshalling and serialization between the machine, and also you can do it in an asynchronous manner. So Spark assumes that most communication have to be blocking and waiting for all the nodes to communicate either to the driver or to each other before moving on to the next stage. In the model of a parameter server, you assume communication happen rather independently from each other, and they do not need so much synchronization, which is one of the benefits in terms of performance from these frameworks. But since you do not have this benefit of being able to synchronize the task and being able to track how they are being done by Spark, you lose a lot in reproducibility and determinism. So then it's really up to you to decide whether it's worth or not. I found this quote from Léon Bottou, which said that as far as performance is concerned, reproducibility is worth a factor of 2. Personally, I think that being able to reproduce what you're doing is worth probably more than closer to 10. But it depends really on what kind of model you are building here. Because if you're trying to build a quick model, and especially in deep learning, in which you know that it is going to follow a very noisy algorithm in the first place, maybe losing one machine in the process is not going to have a tremendous impact on the final result. And if you're unhappy, you can always rerun it when you do that. So there is definitely a lot of space here for exploration and being able to see how to fit Spark and some asynchronous deep learning frameworks. And it's definitely an area of research here. So one of the key elements to make high performance deep learning in Spark is how you communicate between the two. So in a general pattern that you probably all have seen before is to store the data first on a reliable storage. So typically HDFS, S3, and so on. And then using the local hard drives or SSDs to cache some of the data, typically in files, or using Spark's data frames and persistent layers. And finally, if you can put your data in memory, then this is where you have the fastest access. So first, if you can find, really, if you use, whether you use a Python interface or directly you try to embed your computation inside Spark, finding whether you are constrained by communication or computation really determines how you should lay out your data first. Because for a lot of tasks, the data, even though here we tend to think of Spark as being a big data platform, a lot of data is simply not big. And if you're working with a NIST, a couple of less than 100,000 images, then you can probably fit all of that now on a fairly large machine without any problem. If you're working with ImageNet, hundreds of millions of images, then that's a different story. And so this is particularly important if you work with through Python, using PySpark, for example, because in this case, you do not want to put your data in RDDs, since it would take the data from Spark, running in the GVM, serializing it through a network connection to Python, where it would be deserialized by the Python runtime, and then finally being accessed to by the deep learning runtime that would do the computations. All these frameworks in deep learning are heavily optimized for files IO, files input-output, and they all have very good primitives for dealing with files. And it is always easy to forget how good file systems have become nowadays, especially with respect to paging and caching. So you can rely a lot on putting files on your disk and let actually the file system care about how the data is being accessed from the SSD files. And of course, so this is if you use PySpark or Python-based solutions. If you happen to use one of the wrapper libraries that have been developed, then everybody has a different way of doing it. The two main patterns I've seen from looking at the code is either using actually files, so reading, for example, having dedicated readers from HDFS. This is typically what Caffe on Spark is doing, or trying to integrate directly with data frames so that the data is directly piped from its raw representation data frames into the deep learning framework. So since we're talking about performance, let me have a quick detour here to talk about GPUs. So usually we associate deep learning with GPUs, and the reason being is that the deep learning frameworks are really compute intensive, and for the neural network structures, they can be a very good fit for GPUs. So if you look at Spark, a lot of work has been done to make sure that you can take the source code of Spark, and you can compile on a lot of very different platforms. For example, well, you mostly need, if you want to compile Spark, a Java virtual machine, a Python environment, Maven, and a couple of other small things, which is pretty small. GPUs are exactly the opposite. They require specialized hardware. They require specialized libraries. So if you use for NVIDIA GPUs, for example, it requires CUDA, CUDNN for neural networks, CUBLAST if you want to do efficient BLAST operation, linear algebra operations. If you use the Intel hardware, then you need also its own set of libraries for this hardware. So it's really hard to put together a stack that works well. And it is very easy to prototype on one machine. But if you work on an environment in which you may have different versions of hardware, different versions, and if you want to do upgrades, then it becomes really hard to provide a package. So we found that providing a simple interface for the users really helped in that respect, because in the case of deep learning, if you want to use GPUs, you need to provide all the elements of this stack to work correctly. And being able to provide instances with pre-installed drivers and putting all the dependencies inside a container, so being it Linux containers, NVIDIA Docker, for example, solutions, really helps in letting people experiment fast with GPUs. So let me briefly touch the topic of monitoring. If you have run any long-running task in Spark, you know how much of a black hole it can become. And it's especially in deep learning, you want to be able to monitor your tasks. So at the solution, so there's no really good solution as of yet, and it really depends on the granularity of the communication that happens between the deep learning framework and Spark. if you happen to run a small task, for example, if you use Intel's Big DL library that can launch a lot of tasks during training, or if you happen to do big transform in the case of ETL, then Spark can provide you some mechanisms such as accumulators. Otherwise, you are stuck with having to add external information inside the very long-running task to understand what is happening inside. So if you use accumulators, which is a solution provided by Spark to understand what is happening inside the task, they provide you some limited information about what is happening, such as the throughput or failure rates of a task. Their API is primarily designed for Scala. They have some limitation in Python, especially you cannot name them and see them in the Spark UI. And mostly, they do not provide real-time update, in the sense that you have to wait for a task to finish before you will see the update on the accumulator. And this only works if you're able to decompose your computation to have enough of a granularity to see this information. Otherwise, we have seen a couple of people trying to plug to plug an external system. So there are a couple of existing ones that have been developed for Spark. Typically, it is Grafana, Graphite, Prometheus, but there are a couple of other options. They're definitely much more flexible. They plug directly into the metrics API embedded into Spark, but you need to be able to deploy them, to configure them, and they add an extra dependency on your setup. So to conclude, really these days, deep learning is evolving really fast. All these bindings are also evolving at a very fast pace. And it is really very exciting to watch how this space is starting to move. So one lesson that I really found is every insight that you developed so far is really specific to a task, a data set, and a specific algorithm that you use. So nothing will, for now, replace being able to experiment fast with different algorithms or different configuration to see what is happening. And this is why providing an environment in which you can easily swap and plug different frameworks or different algorithms is really a great advantage. And as a developer, as a user, when I get asked the question, I'm going to start to use deep learning, what should I do? Really, nothing beats trying to get an easy start first with one job, then a few parallel jobs using, for example, Python, and then, if the costs are worth it, trying to move into complexity by using these distributed frameworks. So when should you move to such frameworks? Usually it is when you have either too much data or not enough patience to see your job finish on time. That's usually the good threshold to start thinking about it. So now, for developers, there is definitely some gaps in the coverage of Spark to address that would be nice to address to use deep learning efficiently. One of them is being able to monitor long-running tasks. There has been some ongoing discussion in the mailing list about that. And also, MLlib doesn't provide, as of yet, a way to introspect and look into intermediate results and being able to modify current computations. And that's definitely also another area that, for which we would like to see more work being done. And if you are a developer looking at writing or improving a library for combining deep learning and Spark, there are really a couple of questions that you need to ask before starting. The first one is, where do you want to put your boundary between Spark and your algorithm? Do you want Spark to manage your algorithm? Do you want Spark to manage the communication? Or do you want to build actually your own framework that is independent of Spark? Because this will let you implement very different algorithms depending on what you do with different performance characteristics. And finally, I think one field that we're going to see, for which we're going to see a lot of changes this year is, and as Mate was mentioning this morning, is how to integrate Spark with low-level libraries. So how to make sure that Spark doesn't act as a hindrance when trying to make all these different frameworks talk together and how they can be glued together. So we have published a couple of blog posts on deep learning and GPU that explain how you can set it up either inside a public cloud or on your own deployment. And otherwise, I also have some office hours today at 3:50 at the Databricks booth. So thank you for your attention, and I think we have time for a couple of questions.
Yeah, so guys, just before we wrap up, well, let's give Timothy a big hand. Yeah, just a couple of questions from the crowd, if you would. Yes, go ahead.
If we divide up deep learning into the training phase and the execution phase, the part where Spark can be very useful is executing the deep learning models on real-time data. So we can still do the training on the GPU. So is there any plans to integrate Spark streaming data with deep learning models?
Yeah, so the question is whether we can integrate the Spark streaming with deep learning models. So yeah, it's a very interesting topic right now. So the way we see the Databricks is that deep learning, as I mentioned before, making a deep learning framework is extremely hard, and it should not become a dependency of Spark itself. However, what we'd like to see is good APIs to be able to do data transfer between Spark and these frameworks. And if we follow the data frames, APIs, and guarantees, then everything that you can do on data frames will be able to be used on the streaming data frames.
All right, one more question here.
Yeah, so
Should be.
I have looked at the deep learning documentation the Databricks provided, and it seemed like for MXNet, Cafe, and a bunch of others, at least the documentation only talked about how do the deep learning training on the head node.
Mm-hmm.
I wonder if you can talk about, or at least maybe follow up, produce some documentation or sample notebooks on how the training phase can actually happen on the worker nodes.
Yep, yeah. So yeah, how do we combine the libraries, all the libraries for to run on examples? So one could use simply their pattern interface, but that comes at a heavy cost in terms of performance. In this case, it seems that for now, for each library, you need to develop some specific wrappers, which is why we haven't tried to push too much into it. There are definitely some wrappers for doing that for TensorFlow. As for the other libraries, it would be nice to see how we can federate these efforts so that we don't need to reproduce all the same all the same communication patterns. I think this is going to be an effort within Spark itself to see how we can expose more of this API to limit the amount of code that needs to be reproduced for each of these wrappers.
One more question here, Timothy.
Tim, thank you for the presentation. My question is about TensorFlow for R, which last time I checked is still not available for Windows 10. Do you know when that would be available?
So you are the first person whom I hear using Windows with TensorFlow.
Really?
I'll be very happy to chat with you.
It's pretty convenient to have everything on Windows. I mean, I do use Unix.
I suspect you're working at Microsoft.
Thank you.
So yeah, I'll be very happy to chat more about the Windows support after this talk if you want.
All right, any more questions? All right, thanks very much. Let's give Timothy a big hand.